Let's continue our past work with matrices. In this section, I'll show some algebra of matrices and expand upon some properties of the determinants. Contents. Previous videos, I showed the equivalence of Cramer's rule and Gauss elimination. I also introduced the determinants and the determinants as the numerator and the denominator of the expression in Cramer's rule. In this video, I'll expand upon the determinants using algebra. We'll figure out, try to understand and explain why we use the determinants against the previous algebraic expressions that we were using. How determinants expand by rows and columns and still the value stays the same. Let's look at the algebra on this one and reason why a cofactor is equal to -1 times the minor. Let's put it this way. Reason why the cofactor is -1 to the power of I plus j, where I plus j is the index of the ith row and the jth column. And that entire content is multiplied by the minor. Alright, so we've been talking about Cramer's rule from Gauss elimination, and we came up with these expressions where x is the result of the variable, and that result was expressed as the ratio of two determinants. The top determinant has the k values replacing all the a values, a is being the coefficient of x, and the bottom right here is the denominator with the same values as the coefficients a1, b1, c1, a2, b2, c2, a3, b3, c3. Now, interesting question was, why are we using these ratio of the determinants and what is the benefit of these compared to our original equations? If you will look at the past few videos, you will note that if any of these coefficients, either a1, b1, c1, a2, b2, c2, or a3, b3, c3, any one of these is 0, then we end up with a problem of division by 0 in those equations, and hence if we simplify those to being the determinants, then that problem effectively goes away, and therefore that's one of the reasons why these expressions are more suitable and solvable. Another thing that I wanted to point out was the minors. The minor expression, say for example, the minor expression for K3 right here is these four values: B1, C1, B2, C2. Now, for a larger matrix, which is n cross n, the minor will be the matrix with n minus 1 times n minus 1. That would be the minor for one coefficient, where the row and the column for that coefficient are taken out. Say for example, next case, if we want to find out the minor for, let's say, K2, then the minor for K2 would be B1 C3 minus C1 B3. Now note here that the minor uses the sign convention, where moving this way is positive and moving the other way is negative. So in that case, it would be this value right here multiplied by this value minus this value multiplied by this value. This is just a sign convention that is born out of the algebra that we have done before, so it's no big magic here. Another thing was pointing out the cofactors. Let's say for example, and why do we need the cofactors? The cofactors are actually the matrix with the sign reverse if the index that is ith row and jth column, the sum of these two is odd. If that index is odd, then the cofactor is the negative of the let me write it down here, cofactor is negative of the minor. So let's say, for example, the cofactor for let me find it out. Where's the mouse? Yeah. So cofactor for A3. So cofactor for A3 would be C1 B2 going opposite of this C1 B2 minus B1 C2. And similarly, the cofactor for B3, let me change the pen, it's getting messy here. The cofactor for B3 right here would be C1 A2 minus A1 C2. Let's practice a little bit more with expressions for Z. Let's say, for example, if you want here Z again is represented as the determinant of the original matrix where C1, C2, C3 are replaced by K1, K2, and K3, and the denominator has the original matrix with A1, B1, C1, A2, B2, C2, and A3, B3, C3. Now here you can see that the minor for A3, that is M13, is B1, K2 minus K1, B2. And let me draw it. B1 K2 minus K1 B2, and the minor for A1 is right here, B2 K3 minus K2 B3. Now note that 3 plus 1 is even, 1 plus 1 is even. That's why we are going in this direction. Let me draw the directions here. Direction is like this. This is plus minus the multiplication of these two. Minus. So if you move in this direction, it's plus. If you move in that direction, then it's minus. So this is just the strategy or the method that matrices are using, but you can see from previous videos that this is born out of the algebraic equations. There's nothing magical about it. It's just that this is algebra that is fixed and known and tested. Now again, let's look at the cofactors. So cofactors, let's try again a cofactor for, let's say, B3. The cofactor for B3 would be, take all of these, take one column out and one row out, and it would be the cofactor. Here again, let me write it down. This is the cofactor. So the cofactor would be the opposite of the minor in sign if the index is odd. Say, for example, in that case, that would be C1 multiplied by A2 minus A1 multiplied by C2. See, C1 A2 minus A1 C2. That's the opposite of the minor. All right, so let's move on to the next page. Brings us to use the highlighter here. This brings us to the properties of the determinants. The properties of the determinants that we have seen here is that the determinant is the coefficients multiplied by the minors with the signs as given, alternating plus and minus. And if you can change these minors to cofactors based upon the index of this coefficient, it would give you it would help you add all of these together with this minus sign changed right here to this plus, because this cofactor is the negative of this minor. Now the last one, the third one, is actually determinant expansion by rows is the same as determinant expansion by columns. I have expounded upon this in the couple of next slides. Let's take a look at that. And this one is pretty simple, that if any one is 0, then you can expand by 0, either the row or the column, and the determinant would be 0. And another one is that either row or column is a repeat or multiple of another, then the determinant is 0. Alright, so here are some past results for determinant of a matrix. Here we have determined the past results from the expression for Cramer's rule. We could find z as the numerator here, the numerator expression, divided by z as a denominator expression right here, also known as a determinant. Similarly, we can draw these expressions for x and y. From z, I could get the if I take the column A as the divisor during the Gauss elimination, then I can get this column A multiplied by C3B2 by its corresponding minor, and column A2, the coefficient A2 multiplied by its corresponding minor. Similarly, if I use the divisor as B1 in the beginning of the Gauss elimination, then I end up with this expression. And similarly, if I use C1 as the divisor, I start the Gauss elimination by column C1, then here is the expression that I would end up getting. Now all these expressions are the same as this one. We'll see how. Let's move on to the next slide. In order to check all those expressions, what we did was, or what I did was, I used the same old matrix that we had right here. This one, 367 times x gives 367, 842 times y gives 842, and 235 times xyz gives 235. I've been using this as an example, but as I mentioned before, you could have any numbers right here, and these algebraic equations will stand the test. So from the first expression, I've a1 into the minor minus a2 into the minor and a3 into the minor. I put these values right here. I substitute these values. For c3, I substitute 5, b2 is right here 4, right here into b2, c2 is right here 2, b3 is right here number 3. So with all of these, I substitute these and finally come up with this answer as minus 62. Now instead of these a1s, if I were to, let's say, if I replace the ai by ki, that is, if a1 were to be replaced by 367, a2 were to be replaced by 842, and a3 would be replaced by k3, which is 235, I get 6200. Following Cramer's rule, divide the numerator by the denominator determinant, and I end up getting the value of x as 100. Similarly, the expression for b1, I replace the b1 values by these k1 values. k1, b2 values by the k2 value, b3 value by the k3 value, and I end up getting a value of y as 10, dividing the numerator with the k1 by the denominator, which is the determinant of the original matrix. So it makes sense to see the minus 62s right here corresponding to this value and this value. Here's it 62. But you could see that the value of y is 10 because the top expression, which is the numerator, is also the same sign as the bottom expression. So it makes more sense to use the absolute values of the determinants, given that these algebraic expressions are true and tested with time. Therefore, we can use these algebraic equations, which means that the algebraic equations are correct. So this is one of the reasons why we use the absolute values of the determinants in determining these expressions, determining these values for x, y, and z. The determinant expression by that was the determinant expression by by columns. We could also expand the determinant by rows, and the answers would still be the same. Now, this is nothing new about it. All I've done is, if we go to the previous slide, you would see that this value right here is the same. A1 into C3B2 minus C2B3 A1, when I expand it right here, multiply by the minor right here, it is this factor is the same. Now the point is about these factors. Where did they come from? They are simply the rearrangement of the equations for from the first expression. I could easily rearrange those and get this expression. So you can try it yourself. Go back, copy both the expressions, and then redo this equation and redo the first expression. The first expression, this expression is the same as the previous expression used just a while ago. Similarly, for the second expression and the third expression, you can easily reorient the determinant expansion by columns into determinant expansion by rows, and then feed in the values. Now here there's a little bit of a part of a tricky thing, that for the expression for x, you would represent all the a's by k's. That is, a2 right here has to be replaced by k2, a2 right here has to be replaced by k2, a3 right here has to be replaced by k3, a3 right here has to be replaced by k3, and a1 right here has to be replaced by k1. So once you do that, you can easily get x is equal to 100. Similarly, here b1 has to be replaced by k1, b2 here has to be replaced by k2, and b3 and b1 right here have to be replaced by k3 and k1 respectively. Now that tells me that you can expand the determinant by the rows, you can expand the determinant by the columns, and the algebraic equations are correct. They can be rearranged. That is, these two can be rearranged in expression 1 to give determinant expansion by columns. This one and this one can be rearranged in to get determinant expansion by columns, and these this expression and this expression can be rearranged. So that means that determinant expansion by rows and columns is equivalent. We also put in the numbers and we tested, and for both the cases we can get the right values as expected. So in summation, I have introduced the determinants as algebraic expressions, expanded them by rows or columns, and then I tested the expansion by rows and columns, and still the value of the determinants as well as the value of the unknown x, y, and z values stays the same. I showed the why of the Cramer's rule using the algebra as to why do we need Cramer's rule, that is to get away from the zero division. We checked the expressions from the Cramer's rule with known values of the variables, and finally we explained why we have to use the alternating plus and minus signs in the usual equation for the determinants. Also introduced the cofactors and the minors. All right, thank you. See you again. I'll prepare another one and be back.